All right, so we're in the chapter on vapor power cycles. We covered last time the Carnot as a review, as a benchmark. Why do we talk about the Carnot vapor power cycle? It's not practical. You can't build a Carnot vapor power cycle. There's nothing like that, but it's the gold standard. It's the benchmark by which we compare. And then we move away and we say, let's try and make it a practical Carnot, as close to the Carnot as possible, with a real pump that wants water into it, like saturated liquid coming into it. Well, then we move into the ideal Rankine cycle. We can still have maximally efficient turbine, maximally efficient pump, all the devices being internally reversible, no friction, no pressure drops, things like that, but we still see that our thermal efficiency has fallen. The thermal efficiency of the ideal Rankine is less than the thermal efficiency Carnot. True? Then we want to look at how to improve the efficiency starting from the ideal Rankine, the practical Carnot. And we'll take a look at a number of those techniques today. So let's do a quick comparison of what we covered last time. What about the Carnot vapor power cycle? It's made of 4 components. What's the first component? Maybe a boiler. And then we have a turbine. And then we have a condenser. And then we have a pump. True? And the fluid flows out of the pump into the boiler, out of the boiler into the turbine, out of the turbine into the condenser, out of the condenser into the turbine. We label states. Maybe we call this state 1, state 2, state 3, state 4. And then we try to say, we want all of the heat that comes in to this boiler to come in at the high temperature TH. The only practical way to have that happen is for when all of the heat is coming in to the working fluid and the working fluid doesn't increase temperature, the only way for that to happen is it boils. At constant pressure, it's going to change phase. So in order for it to boil, the lowest it can come in at is saturated liquid. So we're going to say that this comes in at saturated liquid for the Carnot. And the highest it could come out with the most energy, the highest enthalpy at constant pressure, the same temperature throughout that boiler, would be saturated vapor. Okay. Then when we expand it through the turbine, we're going to find, oh, we're in a 2-phase region. Oh, it's a relatively high quality, maybe 70-80% quality. And then we're going to condense it. We're not going to condense it all the way. Hence, we'll condense at the constant temperature and reject heat all at a temperature, a low temperature TC, which is the saturation temperature at that condenser pressure. Just like we're bringing all this heat in at TH, that's that high temperature, the saturation temperature at the boiler pressure. What was the equation for solving for, let's say, the work out of the turbine? Well, we're going to get the work out of the turbine in terms of the change in enthalpy. Comes in high enthalpy, goes out low enthalpy. How about the heat that's rejected in the condenser? It's in terms of enthalpy. The heat transfer out of the working fluid in the condenser per unit mass of the working fluid flowing through the condenser is a change in enthalpy. Comes in relatively high, goes out lower. And then the work of the pump, I'm going to try and draw it here so I can see it a little better. The work of the pump into it is H4 minus H3. And then I need to make a little room here. Let me call this QB. QB is equal to H1 minus H4. And that's all coming in at a high temperature TH. True? All right. Then we can sketch this cycle on a diagram just to get familiar. On a temperature entropy diagram, put the dome, put a line of high pressure, put a line of low pressure, and state 1, saturated vapor. State 2, isentropic expansion. So it's constant S from high pressure to low pressure. State 3, we stop it such that when we put it through this very special pump, we're back to state 4, which is saturated liquid. Okay. Some parameters of interest that we would want to solve for would be the thermal efficiency of the cycle. The thermal efficiency of the cycle is the net work, which is the work of the turbine minus the work of the pump, divided by the heat transfer in. Heat in is only from the boiler. And then we want to also calculate the back work ratio. What's the back work ratio? It'll be the percent of the work out of the turbine that has to go back to feed the pump. So the work of the pump divided by the work of the turbine. We know that if we do the math correctly, this will boil down to 1 minus Tc over Th. True? Make sure you solve a couple problems and convince yourself of that fact. It's really neat to see that worked out. Okay. Then we said, well, that's not practical. We still, for the ideal Rankine, we'll still have a boiler. We'll still have a turbine. We'll still have a condenser. And we'll still have a pump. So essentially the same 4 components, each of them doing essentially the same job. It's just that for the Carnot, that pump, we can't buy a pump like that. Pumps like to ingest liquids, saturated liquids. So when we draw the cycle and introduce our states of state 1, 2, 3, and 4, we'll say that state 3 is saturated liquid to make that pump happy. Saturated liquid. Where was saturated liquid for the Carnot? State 4. That's kind of a magic state 4 and a magic state 3 and a magic pump that doesn't exist. This is practical. We can actually take a saturated liquid out of a condenser, that makes sense. Put it into a pump, that makes sense. And whatever comes out is going to be compressed liquid or subcooled liquid because it's going to be a lot lower temperature than the saturation temperature at its high pressure. So it comes out high pressure. And then out of the boiler, we'll still have saturated vapor. So we still have our main heat transfers and the Q in the boiler is still the difference in H1 minus H4. The work out of the turbine is still H1 minus H2. The heat transfer out of the condenser is still H2 minus H3. And the work into the pump is H4 minus H3. We still use those equations to calculate those primary work and heat transfers. Let's go ahead and sketch it on a diagram, a temperature entropy diagram. And we'll put our high pressure line and a low pressure line of constant pressure, high and low. State 1, the location of state 1 didn't change. The location of state 2 didn't change, but the location of 3 did change. And the location of state 4 did change. So, the quality at state 3 is, what's the quality at state 3? 0. And last time in the lecture I made a mistake and I said that running very fast at the end, I said, oh, the temperature at 4 is the saturation temperature at the high pressure for the ideal Rankine cycle. Is that true? It's not. It's a lot lower. I know I then, in the next slide, showed how it's only a half a degree higher, half a degree C higher. So every time when we illustrate this by hand, like I just shown, we make T4 look like it's a lot higher temperature than T3. In practice, it's a lot lower delta T. There's a small delta T between T3 and T4. Half a degree C, 1 degree C, 1.5 degrees C, small delta T. T4, though, has the high pressure. I mean, the pressure at 4 is high. So now, when I put it into the boiler at 4, going into the boiler, it's heated, 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 heated. True? So it's being heated, 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 heated. Not the pressure, it's not changing. The pressure is constant. But finally it gets to the temperature at which it's ready to boil. And then as you heat it some more in the boiler, the temperature doesn't change, but it undergoes boiling. Okay? Makes sense? All right. So when we show the temperature difference between T4 and T3, that's grossly exaggerated on our illustrations. All right. What about the equation for the thermal efficiency? Has that changed? Is it still work out of the turbine minus work back to drive the pump divided by the Q into the boiler? It is, but it's no longer 1 minus Tc over Th. And what about the back work ratio? Is it still the work to drive the pump divided by the work coming out of the turbine? It still is. So one of the things I like to do at this point is I like to compare the Carnot with the ideal Rankine. And I like to say, if I talk about setting the pressure of the boiler is equal to the pressure of the boiler. Don't change boiler pressures. If we're going to compare things, let's compare them where they both have 8 megapascal boiler pressures or 10 megapascal boiler pressure, something, but they're the same pressure. Likewise, the pressure in the condenser is the same as the pressure in the condenser between the two systems. Okay. And now you could go around and you could just say, well, how does the temperature at state 1 compare to this temperature at state 1 for the Carnot? Is it greater than the ideal Rankine, equal to, or less than? How does it compare? It's the same. So the correct answer would be say, they're the same temperature. And then you go like this. You say, what about the temperature at state 2? Is it greater, equal, less? They're the same. They're the same. And then the temperature at state 3. Greater, equal, less, temperature at state 3. Temperature at state 3, same. Temperature at state 4, greater, equal, less. It's less. It's less. The Carnot is lower temperature. So we got our pressures right. We got our temperatures right. Okay, that's great for comparison. And then we just keep going through the system. We say, well, what else is important other than the temperatures and pressures? We could talk about the enthalpies, the enthalpy at 1 versus the enthalpy at 1, which... Oh, I drew this wrong. Okay, sorry. Yeah, that's right. To temperature 4, Carnot is higher than the temperature for ideal Rankine. What about the enthalpy at state 1? Same. How about the enthalpy at state 2? Same. Enthalpy at state 3? The Carnot is greater? Is that right? Okay. And then the next one will be a clicker question. H4 for the Carnot versus H4 for the ideal Rankine. Answer A, it's greater. Answer B, it's equal. Answer C, it's less. So answer A, B, or C, and I will start it right now. So don't call it out. This is now, you compare the enthalpy at state 4 for the Carnot. Is it greater, answer A, than the enthalpy state 4 for the ideal Rankine, or equal or less? All right, let's see where we're at for the results. Okay, well, we're not 100%, but the enthalpy is a measure of the energy content for the fluid. The definition of enthalpy, H, is U plus PV, true? And so you could think of it being high because of high temperature, and I know pressure and temperature both affect you, but also because of this high flow work term, this high PV term. So when you look at the energy content of the Carnot at state 4, it's higher temperature. I know that they have the same pressure, but it's really the higher temperature that really makes H4 Carnot greater. So if H4 Carnot greater, what was the right answer? A. Good. Now I wish I had more room, but I have to just start erasing some. So you just have to remember we're not changing the compressor boiler pressure or the condenser pressure, but I'm still making this comparison. Now let's walk through this. This property may be less intuitive, S. And we could do S1 versus S1. What do you think? Is it greater for the Carnot, equal, or less? Which it's the entropy at state 1 comparing those two cycles. They're equal. They're the same. So that's the same. How about the entropy at state 2? Is it equal? Less? Okay, equal. Now we'll ask a clicker question. Entropy at state 3, Carnot, versus the entropy at state 3, ideal Rankine. Greater, equal, or less? Answer A is correct, answer B is correct, or answer C is correct. The entropy at state 3 for the Carnot, compare it to the ideal Rankine. Is it greater, equal, or less? Answer A, B, or C. One of the things before I show the clicker responses is you can look at this diagram. If it would be, see where S is right here for the Carnot versus the S is over here. So, does that help? Yeah, right? So the, oh no. I didn't grade that one. So either it was a freebie or a no-bie, but it's redoing it, so get the vote again. You get the vote again. I gave you a hint. Sorry, I hit the wrong area of the screen. So this, I think, will get closer to 100% correct. But it won't quite be 100% correct. It never is. There's somebody that intended to vote for A and hit B. That's true. Did it polling end? Now let's see. Okay, so the entropy at state 3 Carnot, state S3 Carnot, is greater than S3 ideal Rankine, because that's where we stopped and it was Carnot, but now we go further. We throw away more heat. We condense it further in the condenser to come out of the condenser saturated liquid. So, true? 80%? True? Should I ask that question one more time just to move it to 100%? That would be awesome, huh? All right, well, we're going to continue on this game. S4 Carnot versus S4 ideal Rankine. Greater, equal, less? Answer A, B, or C. And I start now. Now we're looking at the entropy, state 4. The Carnot versus the ideal Rankine. Which one is greater entropy? Or are they the same entropy? All right, ready to take a look? All right. There? So what happens is the entropy at state 3 Carnot is exactly the same as entropy state 4 Carnot, because you're putting it through the pump and it's reversible, boosting the pressure. Entropy's the same, right? And for the ideal Rankine, S3 is equal to S4. I know that it's hard to draw it. Maybe on this one it's easier. I just say, look, it's on a straight line, same S, true? Over here, straight line. Well, okay, I didn't put state 4 perfectly above state 3 because it would exaggerate the temperature more than I can. So we're kind of bending the straight line up and down often when we draw it on the ideal Rankine. But, so the answer is the same as the previous answer, A. True? Okay. Now, let's talk about, we finished our temperatures, we finished our enthalpies, we finished our entropies, and now I just need to make some more room here, and we'll start talking about, a little bit harder, but the Q in the boiler for the Carnot versus the Q in the boiler for the ideal Rankine. I'm going to ask a clicker question. Greater, equal, or less? Answer A, B, or C. Which one? This is the boiler. For the Carnot versus the ideal Rankine. Which one is greater? Same boiler pressure, same condenser pressure. True? And we have everybody in. I knew this one would have a greater distribution of results. It's harder to answer this question, isn't it? Isn't that the harder question? So let me try and, well, this is covering it up, so I have to just tell you what it is. And then, let me see, can I make this smaller? It won't let me make the windows smaller. Sorry. So the answer is C. Okay? The answer is C that way. Well, why? Okay, let me get the box out of the way. I tried to show that the heat going into the boiler for the ideal Rankine, first there has to be some heat to get it up to start to boil. That's a lot of heat. It's bringing in subcooled liquid. It's got to take that 60 degrees C water and bring it up to 295. Those are the numbers we threw around last time. That's a lot of energy just to heat it up from 60 to 295 with no phase change. Then from 295 saturated liquid to 295 saturated vapor, a lot more heat comes in this area. But that's the heating that occurred with the Carnot. So that last half is the same. So the ideal Rankine, there's more heat per unit mass going through the boiler. Okay. I knew that would be harder, but let's continue on. What about the work of the turbine, the specific work of the turbine, Carnot versus ideal Rankine? I'll ask a clicker question, okay? So it's greater, equal, or less, A, B, or C. The turbine. Okay. For the Carnot and the ideal Rankine cycle. The specific work out of the turbine, kilojoules per kilogram. All right, let's go ahead and see how we reported this. And it is the same. The enthalpy at 1, we agreed, as a class, was the same between Carnot and ideal Rankine, and the enthalpy at 2 was the same for the class. And so if the enthalpy change is the same, then the workout of the turbine is the same. So answer B was the correct answer. True? All right. Now, I know, somebody's shaking their head going, I can't believe I put A or C. But I told you this joke. It's not a joke. It's a friend of ours in one of the presidential elections said that her sister went into the voting booth, seriously, intending to vote for candidate A, presidential election. Came out convinced they voted for candidate B. And was so distraught. Got confused by having to push the button or something. So just think about that. There's probably at least a fraction of 1%, maybe 1/10 of a percent, that actually get confused in the voting booth walk in intending to vote for A and vote for B or something. That happens in this class. You saw it. You just saw it. You knew the answer. You knew the answer. You knew what you wanted to vote for. All right, let's continue on. Q in the condenser. Q in the condenser. Greater, equal, less. Do you want to do a clicker or just answer it? Clicker? All right, you like those, huh? A. Some people feel they're racking up the points. And some people are feeling like, I want this pain to end. So what happens in a condenser? Which one has larger heat transfer out of the working fluid in the condenser, the Carnot or the ideal Rankine? All right, voting has stopped. Well, the H2 is the same for both cases. We agreed on that. But the H3 is a lot lower for the Rankine. You threw out more. You had to condense it further. So, which one is correct? C. Oh, let me get the thing up here and grade it. Oh, very nice. Only a few people are confused. All right, so that one, like that. And maybe I should put on there, this whole column is Carnot, this whole column is ideal Rankine. Let's do the last one. Work of the pump, ideal Rankine. Work of the pump, Carnot. Greater, equal, less, A, B, or C. And that'll be the last clicker question. Maybe. I'm getting tired of them, aren't you? Okay, we're all done. Well, let me answer this question before I grade it, okay? What do you think? We have the work of the pump. It's ingesting a two-phase. It's having to actually compress it. That will cost a lot of the flow work. Think about that. That'll cost a lot to compress as well as you're boosting the pressure. It's cheap. That's one of the great themes I hope you leave this class with. It doesn't cost us much mechanical energy to boost the pressure of an incompressible substance. Pumps are cheap to run. Air compressors, very expensive. Some other steam compress, with a two-phase mixture, that's going to be more expensive than a liquid. So more expensive per kilogram of substance that's undergoing the pressure boost. So the Carnot pump is more expensive. True? Isn't that what I just said? Am I consistent with what I just said? So we see that it's 73% of the class had it correct. Okay? Yes, sir.
Is it the area to the left of, state 3 and 4 on the TS diagram that shows the work?
On the PV. On the PV, not the TS, right. The area to the left of a PV diagram. But that is only for processes which are internally reversible. Both of these are quote-unquote internally reversible, but to have to know the path on the PV diagram, I have to know the path on the PV diagram to actually make that calculation. And that path on a PV diagram for an ideal gas, I can get analytically. For a two-phase mixture, steam under the dome, good luck on getting an analytic expression. Oh, I can sketch it on the diagram and make it look like, hey, I know that one perfectly. And then I can go into a computer code and make it work, where I can get it numerically pretty well. But analytically, by hand, using the tools we have available, sheet and paper, pencil, not for steam. Air, ideal gas, yes. Also, it's very easy for the incompressible substance because PV is a straight line up. V is constant, and so that's easy to justify. Well, there's a few more I wanted to do. I guess I'll continue this game, and we'll do this. The thermal efficiency of the Carnot versus the thermal efficiency of the ideal Rankine. Greater, equal, or less? Answer A, B, or C. Which cycle is more efficient? Thermal efficiency. Carnot or ideal Rankine? Yeah, it's like 0.3 versus 0.4. You know, I know that 0.3 is lower than 0.4. So either think about percentages or fractions. Either one works. Okay, polling has stopped. Do you think we have unanimity? Pardon? Yeah, the polling is finished. I had it 30 seconds. You just walked in?
Yes. It's my first. I just signed up for that ad form.
Oh, you just signed the ad form? Okay, well, we can talk later, but unfortunately you got to eat the points that you miss out on. Those that are here from the first day of class on. All right. All right. Now, we don't have 100%. What is the gold standard? If you could build a Carnot heat engine to turn heat into work, do it. It's going to give you the highest conversion. You're going to have to burn less coal to make electricity. It's going to be more efficient, more profitable. So which one is correct? A. True? 75%. Where's the other 25%? I intended A all along. Right? Now the back work ratio for the Carnot versus the back work ratio of the ideal Rankine. Greater, equal, less. Answer A, answer B, answer C. We start the polling. All right, polling has stopped, and now we showed the results. And the back work ratio, let me try to explain this real fast. The work of the turbine for both of these, the Carnot versus the ideal Rankine. The work out of the turbine we agreed is the same. And then we said it is so much cheaper. It costs less mechanical energy to run the pump if you supply the pump liquid. Which one supplies liquid? The ideal Rankine. It's compressed, condensed all the way. So, which one is lower? So, true? So that was A. A said higher. So now, which one is good? The efficiency being greater, that's good. Okay? But the back work ratio being greater, that's not good. We don't like that. That's actually for the Carnot, that's bad. This is good. Or I shouldn't say good, bad, I should say better or something like that, right? We want, as an engineer, low back work ratio, high thermal efficiency. Okay? Hopefully that helped. That was the last clicker question for today. You can put them away. I already asked these questions. But let's do this without clicker. For the ideal Rankine cycle, the flow through each component, through the boiler, through the turbine, through the condenser, through the pump, is internally reversible. True or false? It's true. It is true. We're not adding irreversibilities and then trying to compare the Carnot with some cycle that has irreversibilities. No. It's internally reversible. The effect of boiler and condenser pressure on efficiency. We talked about this last time. What would you like to do to the boiler to improve the efficiency? Boost the pressure. Hence, if you boost the pressure, that boiling temperature goes up. So you want to boost the boiler pressure. When you do that, you boost the temperature between 4 and 1, where a lot of heat is brought into the cycle where it's actually boiling. That's the saturation temperature at that boiler pressure. You boost it. Okay. What do you want to do to the condenser pressure? You want to lower it, because when you lower it, the saturation temperature at the condenser pressure goes down. You're throwing away heat at a lower temperature. You're bringing in heat at a higher temperature. Good for performance. Bring in heat into the working fluid at high temperatures. Take heat out, reject heat, throw it away to the atmosphere at low temperatures. That's the theme. That's the theme. How do you improve the efficiency? Well, we're going to start from the ideal Rankine cycle. Use that theme. I'm going to try to bring in more heat at high temperature into the working fluid. Why stop at the end of boiling? Why not continue out and superheat the steam before it goes into the turbine? No, you're going to be good for performance because you're going to be bringing in heat at higher temperature. A larger fraction of the heat that comes into the cycle will be going into the working fluid at high temperature. That's good for performance. The other thing is, it's very practical that when you expand it, you want the last little bit of steam going through the turbine to be high quality steam. You don't want a lot of water droplets in it, because water droplets have much higher density. They're like little marbles or little BBs or little chunks of solid. I know they're liquid, but they act and they hit a blade or they rotate. They may not turn as easily, right? If you have a two-phase mixture of some gas with some particulate in it, typically you make it turn, and the inertia of the solid particle keeps it going, and it goes out to the wall and strikes the wall and is collected. Take a look at different ways to separate out gases that have some entrained solids, or liquids that have some entrained material that has higher density and little particles. One of the things you do is turn it on a side, and the gas is easily turned, and the solids go straight and hit something. So anyway, you don't like that. That's good to get a higher quality at state 2. That's good. So superheat. Good for thermal performance, good for practical steam engines. Okay. So what comes out here no longer is saturated vapor, it's superheated vapor. Here's a problem. We have water as a working fluid in the ideal Rankine cycle, and its superheated vapor exits the turbine. So instead of coming out at 8 MPa, I think that was the same pressure we looked at last time, the saturation temperature is like 295 degrees C, around 300 degrees C if my memory is correct. Now, what you do is you bring it out at 440 degrees C. So it went from 295 to 440 degrees C. That's the amount of superheating. Then you pass it through. And then you still want saturated liquid entering the pump. That's good for the pump. And the condenser pressure is 20 kilopascal. This is the standard format for these questions. Find the work of the turbine, find the work of the pump. Find the heat transfer in the boiler, heat transfer in the condenser, compute the thermal efficiency, and compute the backwork ratio. The strategy that I have is that you sketch the components from memory. What, Professor? You want us to actually memorize? Yes. Put boiler, put turbine, put condenser, put pump. Now, a lot of times they introduce them that way because state 1 is in that upper corner, and then when you put it on a TS diagram, state 1 is up in that corner. And then state 2 is over here, then state 2 is down there. Okay? And then state 3 is over here, state 3 is over here, then state 4 is over here, state 4 is kind of over there. See, so they kind of match the corners, right? 1, 2, 3, 4. So that's one of the reasons that you'll show it like that. So when you map it onto the TS diagram, it looks the same. Okay? Upper right corner is state 1. But a lot of illustrations, what they'll do is they put a tall boiler. Why? Because if you go out to a coal-fired power plant, you look, you say, hey, show me the boiler. There it is. It's massive. It's huge. It's 4, 5, 6 stories tall. Okay, it's tall. Tall building. And then out of the top of the boiler, they bring it over and they pass it through some turbine. And out of the turbine, they put it into a condenser. And then they always put the pumps. Where do they put the pumps? Low. So they put the pumps low. The basement. There you go. So they'll sketch it like this. So boiler, turbine, condenser, pump. Okay? They didn't really change much. It just, that's the way they'll sketch it on an illustration. And they'll have state 1 coming out of the boiler into the turbine, 2 out of the turbine into the condenser, 3 out of the condenser into the pump, 4 out of the pump and into the boiler. I recommend we make a table of properties. Did I do that last time? Say state 1, then 2, then 3, then 4. And then I say critical pressure, or not the critical, but the important properties start with pressure, kilopascal, megapascal, or bar, either one. Temperature, degree C, Kelvin, either one, or both. Quality, I like to put there somewhere. And then I sometimes will put specific volume, sometimes not. I don't really need it. Enthalpy in kilojoules per kilogram and entropy kilojoules per kilogram Kelvin. I know that I'm going to be playing with those properties, H and S. So then I say fill up my pressure first. So pressure at state 1, that's my high pressure. That's my 8,000 kilopascal. Pressure at state 2, that's after the turbine. The turbine, there's a big pressure drop. 20 kilopascal. 20 kilopascal out of the condenser. Then the pump boosts it back up to 8,000. This boiler is constant pressure just like the condenser's constant pressure. True? So we get those down. Okay, I can't erase. Then what we do is we look for information that helps fix the state. Sometimes we know the temperature. This temperature was given to us as 440. True. Now, most of the time, when you condense on a TS diagram, when you condense on a temperature entropy diagram, and you have some slightly superheated steam, when you condense, when you go through the turbine before you get into the condenser, it's still a high quality steam at state 2. But let's say you really superheated it. There's a possibility it could be superheated vapor. That's not good for performance. Engineers don't want to do that. They would like to get state 2 kind of tucked up into this region right in here. High quality, but we got a lot of energy out of that steam. Some of the water is in the form of droplets. Okay? Okay, but theoretically, if you way superheated it, go state 1 way out here, state 2 could be superheated vapor as well. So what about if I know the pressure and the temperature, 2 independent intensive properties, I can go and get the enthalpy and the entropy at state 1. But what fixes state 2? It's isentropic flow through that turbine, true? So it goes pressure and entropy are what I use to fix the state 2. So this entropy is right there. Once I know that, I can look up H. And I often find that entropy is between S of F and S of G at that low pressure. Hence, I look up the quality, calculate the quality, then I calculate H. And T is T sat, the saturation temperature at that low pressure. Did that make sense? I hope it did. What about state 3? It's saturated liquid. at that low pressure. So the quality is 0. It's saturated liquid. So I can look up Tsat at 20 kilopascal. I can look up HF and SF at that low pressure. Should I write those out? Is that helpful if I say this is SF and this is HF at that low pressure, and this is Tsat? Okay. Then what do? We put it through the pump. State 4 is very, very close to state 3. We exaggerate that temperature difference. Well, how do I do this by hand? Well, what I typically do, or what the book does and a lot of textbooks do, is they say, if you're doing this by hand, we know that we can calculate the work of the pump easier. It's V dP, P4 minus P3. What is this V? Well, it's constant. It's incompressible. Why don't you just pick 3 as the input, the specific volume of the liquid, saturated liquid coming in, state 3. Multiply that by delta P, you've got the work of the pump. Does that look good? Have you seen that equation? That's what we were just talking about. You asked that question, hey, isn't it the area to the left of the curve on a PV diagram? That's what we're talking about, right? It's easy to compute when you have a PV diagram and it's low right here, and all you're doing is going up in the little bit of area between state 3 and state 4, because V doesn't change. V is a constant. It's small, it's liquid, boom. So it's the integral V dP. All right. Once I know the work of the pump, well, H4 is equal to H3 plus the work of the pump. You agree? So we can just put in H4. We know this S is the same, but we used it because this applies only if S is constant. Okay. And it is approximation because V truly isn't exactly the same. I mean, that's a little bit of an approximation. So, but we like approximations that work very well, and that works very well. What temperature is this at? Well, it's about T3 plus about 1 degree C. Okay. How do I get that out of the tables? Good luck. It's better out of a computer code. And I can show you, we'll do that later today. How to do this in Excel with the software that you can get. Now, once I have that table of properties, then I usually have another table of all of my, let me get rid of it over here, kind of tuck it in here, I put all of my Q's and W's, Q of the boiler, W of the turbine, Q of the condenser, W of the pump, and I know that those are all delta H's, and I make those calculations. And then I continue that column and I say, okay, I need to calculate the work of the cycle, the work net of the cycle. I usually calculate that. Q net of the cycle, I usually calculate. And I compare. If they're different, I have an error. I look for my error. If my Q net doesn't equal work net, I messed up somewhere. And then I compute the thermal efficiency, and the back work ratio. And so you've seen that, kind of looking backwards, that's what we've done. We've calculated everything. Okay? Yes, sir.
Is state 2 and superheated?
State 2, the way I have it up here remaining on the illustration, would be superheated, but most of the problems are going to have state 1 not that superheated. State 2 will be a high quality steam. Yeah, for the ideal Rankine, what we'll do later is we'll say, oh, and the turbine has an isentropic efficiency of 85%. Guess what? You got 2 steps in that now to handle that 85% isentropic efficiency. Make sense? Here is that problem with the numbers from an Excel file showing you. So I have it up here. Primarily, you can record. The lecture is recorded. You can go back and pause it at this point and then study these numbers. And you can actually do them by hand. You'll get slightly different numbers in the tables in the back of the book because the software that I'm using is from a different source. And they're slightly different.
What was the quality for state 1 and state 4?
Okay. Let's go ahead and plot this on a temperature entropy diagram. Let's go ahead and do that. I didn't show those points out there. But point 1, state 1, has a 8,000 or 8 megapascal and 440. Well, there's around 440 temperature, so it's somewhere along that line. And it's an 8 megapascal. I have a 5 and a 10 megapascal. That looks like an 8 megapascal line. Right there is state 1. Is there a property known as quality that's defined for state 1? No. Don't give me a quality for state 1 because it's superheated vapor. It's not defined. Quality is defined between saturated liquid, saturated vapor. True? So that I would put right here, not applicable. Well, you know, the computer code don't know that, not applicable, so I just leave it blank. Now, if I put in there, I don't know what the software would return. The software may return 1. I don't know what we can try it in a minute, what the software would return. Or the software might barf on us and say, oh, you made a mistake, we can't do that. I don't know. So whatever the coder did. Then, where is state 2 on this temperature entropy diagram? Well, we're down to 20 kilopascal line. Here's the 20 kilopascal line. True? And state 1 and state 2 have the same entropy. And this is the entropy axis. So where is state 2? Where is state 2? Right there. And now where is that point? It's in the two-phase region. And this code said that the quality at state 2 is around 80%. You could superheat it a little more. Superheat it out to, I don't know, 500, 540, 600. And see, as it nudges out, maybe gets up to 85, 90, 95%. But don't superheat it so much that it comes way out here. That's not good for performance. Okay, that's state 2. Where is state 3 on this diagram? Way over here, state 3. Where is state 4 on this diagram? I mean, so close to state 3, it's ridiculous. I can't even see it. I have to zoom in to see it. And this code allows me to compute the difference in the temperature. So the temperature at state 3 is 60.1 degrees C. The temperature at state 4 is 60.4. That's a smidgen above, right? I have no idea what a smidgen is, but it's a small amount. Okay? Yeah. Okay. Now, I put this in for interest also because if you wanted to compute the work of the pump, you could use the specific volume at state 3. The work of the pump is V sub 3, this V right here, times the pressure difference, P4 minus P3. Let's do that if you have a calculator. 0.00102 meter cubed per kilogram times 8,000 minus 20 kilopascal. And then you have to recall, okay, kilopascal times meter cubed is a kilojoule. So this converts right away to kilojoule per kilogram. Let me repeat that. A meter cubed times a kilopascal, chase your units, do this a few times, convince yourself it's precisely 1 kilojoule. Do I have to memorize that, Professor? Well, some things are really nice to know when you want to take a test and it's timed, right? Work that out, develop confidence, and use it. Okay, so shall I repeat that one more time? Unit conversion. It's a great unit conversion. 1 meter cubed times 1 kilopascal is precisely 1 kilojoule. I made that kilo look bad, but it's a kilopascal. 1 meter cubed times 1 kilopascal is precisely 1 kilojoule. I don't believe it, Professor. Okay, this is the way you prove it. You say, give me a new page. Where's my new page? You insert new page. You start this. 1 meter cubed times a kilopascal is equal to 1 meter cubed times a kilopascal. My computer's having trouble keeping up with me. Okay, kilopascal. Is that equation correct? Yes. Do you have confidence? You have to start where you have confidence. All right. And then you multiply by a unit conversion. I recall that a pascal is precisely a Newton per meter squared. With confidence or without confidence? Is that correct? Did I just multiply that equation on the right-hand side by 1? Yes, I did. And then we say a joule is a Newton times a meter. True or false? So the newtons cancel, the pascals cancel, leave that kilo right there. And we're left with, the meters cubed cancel. Thank you very much. And so we're left with 1 kilojoule. The kilo from there, and the joule from there. Done. All right, somebody ran that number. What did we get for the work of the pump? 18 point something? 8.139. Okay, well, this is the answer that the computer gave us. I think they agreed at 2 digits. It's good. Okay. How did the computer do it? Well, I just said, make this entropy the same, and state 4 is determined by pressure and entropy. All right? So then over here is the work of the turbine. Notice the units. I remind myself of the units, kilojoules per kilogram. Q of the pump, blah, blah, blah. Now, I did do Q net. Can somebody look at these numbers and calculate Q net? How do I calculate Q net? Well, it's a net heat transfer into the cycle. So it comes Q boiler in minus Q condenser out. So the Q boiler in is 2987.8, and the Q condenser out 1895.8. What does that give me? 1092. There you go. See, that's a good check. Yes, sir.
What's your state 0 for?
I often put a flow exergy column as a last column, and then to do that, I need to know the temperature at the dead state. The enthalpy and entropy at the dead state, knowing the dead state temperature and pressure of 25 and 100 kilopascal.
Does that mean before you start your cycle?
Yeah, this is just my convention. You can throw that out, and you can solve it without the exergy. But then I could continue and do an exergetic analysis of this problem as well. The flow exergy is a pain by hand, a severe pain by hand. But it's really easy once you implement it in software. Just trivial. Okay? Oops, I jumped to the next slide. How did I end up doing that? Oh, I jumped more than one slide. Boy, did I jump a lot of slides. You ready to press forward? How else can we improve the efficiency? Well, on this temperature entropy diagram with the dome, and you have really put up a high boiler pressure. It's way up there. And then you have a really low condenser pressure, which is good for performance. But you notice that you bring it out to superheat, but you really don't want to heat it up much higher than that. from metallurgical considerations, practical considerations. So what you do is you say, let's do this. Let's have 2 turbine stages. Let's expand it through 1 turbine stage, out of the boiler, expand it, take it back to the boiler for some additional heating, and then pass it through a 2nd turbine stage, then go to the condenser. All power plants have multiple turbine stages, not 18 of them, but they'll bring the steam back out, back to the boiler, or split it off and do something else. We'll talk about that in a minute, but just do this for reheat. So they reheat the steam in the boiler. So not only do you heat up the steam in the first pass, but you dump some more energy into the steam in a 2nd pass through the boiler. You're reheating it. What's it look like? Well, you're going to have an intermediate pressure, because this is some intermediate pressure. It's not the high pressure, think about 8 megapascal, and it's not the low pressure, 20 kilopascal. Maybe it's a 1 megapascal pressure. There's some pressure in between. So you stop the temperature because of metallurgical considerations. You expand it. Maybe it expands into the 2-phase region. Maybe it expands into the superheated region. For maximum efficiency, probably it's really close to saturated vapor, probably inside the dome. And then you reheat it up to, you could reheat it back up to that same temperature again, and then expand again. Okay? So that's the concept of reheat. I probably should have shown it on a real diagram, but we'll do that in a minute. Right here. That was a short minute, Professor. All right, so 8 megapascal, 440, the same thing we had, but this time at 1 megapascal, take it out of the first turbine, take it back and reheat it to 440. Then, once you come out, put it through the 2nd turbine, and then go back down all the way to 20 kilopascal condenser pressure. That problem makes sense? Same list of things to solve for. But here you got to be careful because you have multiple turbines. You have 2 turbines. And you have 2 heat transfers in the boiler. That's right, 2 heat transfers in the boiler. So here's the solution to that problem. First of all, make a good sketch. So state 1, then 2 is after the first turbine but before the reheat. State 3 is after the reheat before the 2nd turbine. And then state 4, then 5, then 6. Okay? Yes, sir.
That 1, 2A, 1B.
Yeah, they sometimes do that, but what they have done is just renumber all of them. So what comes out of the condenser used to be state 3, now it's state 5. Okay. What goes into the steam generator or boiler used to be state 4, but now it's state 6. So just renumber them all. Okay. Now, later in the textbook, for a different cycle and a different problem, you'll see somebody saying, I really have fallen in love with knowing that this state is state number 3, and I really don't want to change it. Then they'll introduce, it's in our textbook, state X. What? Don't do that. Renumber them. Oh no, state X. Student looks at it. Student says, oh, we have a state quality. Okay. I think it's more. It's better for if you just renumber them. I think. Oh yeah, the real power plant has many states. Yeah. But in our problem, in our textbook, we don't have that many states. Okay, so same strategy. Get a temperature, pressure column going. Get your enthalpies, your entropies. From that, fill it up, populate it. Know how you're working through the table. This is my little helpful reminder column. Oh, state 1 is determined by knowing temperature and pressure. State 2 by pressure and entropy. State 3 by pressure and temperature, etc. And then calculate the works. This is the work through the first turbine. There it is. This is the Q for the reheat. There it is. there's the Q for the first pass through the boiler. Okay? This Q for the first pass of the boiler is H1 minus H6. What about for the reheat? That's H3 minus H2. Okay? And then the work from the second turbine, that's going to be H3 minus H4. And so you calculate all those. I need the work net. I should have calculated Q net, double checked it, but I didn't. You calculate the back work ratio and the thermal efficiency. So by introducing that reheat, you do boost the thermal efficiency a little bit for this cycle. Okay? It's still not back up to where the Carnot is, but you'll never get there. All that makes sense? All right. So that's one way to improve performance. So you have the idea of superheating. You also have the idea of having a high boiler pressure. True? And so here is, you're going to just compare. If I have a pressure right here, a boiler pressure, I'm changing it from 6 to 8 to 10. You could see the trend, 6 to 8 to 10, increasing thermal efficiency of the cycle. Also, if you're at 6, when you come out of the boiler, that's saturation temperature. I don't know the number, but it's between 250 and 300. There it is, the saturation temperature at 6 megapascal. Here's the saturation temperature at 8 megapascal. That was 295. We've been playing with that number. If you go up to 10 megapascal, well, it's a little higher saturation temperature, maybe 310, somewhere in there. Okay? So that's the starting point of these lines. And then what were we showing? We're showing the amount of superheating. So superheating, even at a 6 megapascal, improves performance. So coming out of the boiler, not at the saturation temperature, but at 300, 350, 400, all of that helps. So coming out at higher pressure helps. Coming out superheated helps. This is real data plotted with the software. There's a limit, and often it's metallurgical limits and associated with fatigue and with things failing, okay? And used to be in the history. This is now 150 years ago this year. I was driving to work a couple of days ago because this event happened in April. So April 27th, this year, I was driving to work, and on the radio they say this is the 150th anniversary of the worst maritime disaster in the United States history. It was the Sultana steamboat explosion on the Mississippi River. The steamboat had roughly, they don't know the exact numbers, 2,000 people on it. Almost or right at 2,000 souls gone that night. Steam boiler explosion. You can watch a PBS documentary on it, whether or not it was sabotage. It doesn't look like it's sabotage. You can go read the report on it. Why? Because that's a lot of loss of life. 2,000 people. It's easy to throw a number out, but that's a lot of people. In this room, how many people? 50? Double it. 100? Okay. Double it. 200? Double it, double it, double it, till you get to 2,000. That's a lot of people. Look around. Woo. So, anyway, this was a steam boiler explosion. So, whenever people want more power out, boost the boiler pressure, but then you have problems with fatigue, failure, ruptures, and steam under high pressure really does a lot of damage. It still does a lot of damage. I don't have time, but you can find where I've looked and shown in this class videos of a steam boiler explosion a few years ago. I believe it was in Paris, Tennessee. And it was in a plant. And some of the maintenance people took some of the safety features on the plant. Oh, it's not working. I know how to fix it. Turn it off. Take that safety feature and disable it. Keep running. Hey, the plant's still running. Don't have to shut down. We'll shut down next month, next year. Oh, somebody forgot to shut down and repair that valve. Never got repaired. Anyway, it blew up and it caused a lot of damage. And so this big chunk of heavy metal, I don't know, hundreds of pounds or tons, shot through a building, blew through walls. Didn't kill anybody, I think. I think it was thankful that nobody was there when it blew up. But you still see steam boiler explosions in the United States or in different parts of the world, even today, even though it's not a primary method for transportation like in the 1860s. A lot of boiler explosions in the 1860s. Actually, the history of ASME as an organization, you can read about this off the ASME website. That's where it's copied from. Goes back really to the tragic loss of life when you had multiple steam boiler explosions. And the first real contribution, I know there was other people, players, that insurance companies especially, because they had to pay out with the loss of life. But the ASME boiler and pressure vessel code is still the major big code that ASME puts out. So, and the ASME stamp that goes on a boiler pressure vessel that's made to the standard. You can't put in a boiler without it's stamped, it's certifying that it's made to that standard anywhere. It's just against state laws and city regulations and all sorts of regulations because of the loss of life. If somebody just says, I can build you one, and gets in his backyard, welds something up, here it is. Then you pressurize it and it blows up. Not so good, right? So that's, it's hard to even think about that, but you would have shops and they would just make stuff and put it out in production and it would blow up. So, all right, here's looking at condenser pressure. The challenge with condenser pressure is finding how you reject the heat. And we reject heat to lake water often, or river water, not so much in Texas, or ocean water, not so much in Texas, or actually to the air by evaporative cooling or something else. But often in Texas, our big power plants are located, they build a lake for it, and they reject it to a lake. And that lake temperature is low, but you can't make it any lower. Another way to improve performance is to look back at that heating of the water before it got to the boiling point. There is a lot of heat brought in. And from a thermodynamic point of view, this is brought in at relatively low temperature. Recall that on a temperature entropy diagram? Bringing in heat at low temperature is not good. Bringing in heat into a cycle at high temperature is good. So from an entropy perspective, this is bad. From a second law perspective, this is bad. So what you do is you say, don't bring in the heat from the outside source, find an internal source. And so what they'll do is they'll say, okay, after the first turbine, we're going to go back for reheat. That's a great idea. Let's keep it. But I'm going to take some of this warm steam. It's still high pressure, still warm, and I'm going to do something useful with it. I'm going to use that steam to preheat some of this cold feed water such that what comes into the boiler or steam generator isn't as cold. And that's the idea. I'm going to take from one pocket and put it in the other pocket, but it will improve the performance of the system. So they divert some of this steam down and they put it into a feed water heater. Why do they call it a feed water heater? Well, it's water. It's heating that water, and that water's feeding the boiler. So that helps you. Okay, that's why they named it that. It's the feed water to the boiler that's being heated. And we're going to first talk about an open feed water heater. All you do is take one stream of fluid coming in, another stream of fluid coming in, and let them just mix, and one stream of fluid going out. So the way this works is we already know this is at a lower pressure. Maybe that's 1 megapascal pressure, true? If it just mixes, this really needs to be 1 megapascal coming in, 1 megapascal coming in. Guess what coming out of that open feed water heater is? 1 megapascal. It's just opening up, 2 pipes coming together, they mix, and it goes out in a third pipe. But what do you have to do? You have to get it back up to 8 megapascal, the high pressure, the boiler pressure. So you need to put another pump. So you'll have pump number 1, pump number 2. It's a little more complex system, but if it's worth the payoff, if it improves overall plant efficiency, then that's good. True? So what's the idea behind the feed water heaters? Don't pay for expensive coal to heat all of that low temperature heating of the feed water. Use some other, it's still warm steam, it's still valuable steam, but it doesn't have the ability to make work like it used to, but it can still make something hot very well. So we'll use it to heat up the feed water. So that's what it looks like. The only thing is we have a new equation, and it's for this y. Well, what is y? Y is a mass fraction. So y is defined as the mass flow rate that goes into the first turbine. See, it's like 100% of the steam that comes out of that steam generator goes into the first turbine. And then out of that, some of it splits. It splits. It's so 1 minus y is the fraction that continues to the reheater, 1 minus y. 1 minus y is the fraction that continues to the second turbine. 1 minus y is the fraction that goes through the condenser. 1 minus y is the fraction that goes through the first pump. But y joins up with 1 minus y in the open feed water heater, and now you're back to 100% that goes into the second pump, out of the first pump, second pump into the steam generator. You see that? So it's like 1, and then maybe y is 0.2. Well, then 0.8 goes around until it joins back up. What's 0.2? It's the fraction. It's 20%. What's 0.8? 80%. So what is, it's a ratio of what goes down to feed the open feed water heater divided by the mass flow rate that came into the first turbine. Well, that mass flow rate that came into the first turbine is the mass flow rate through the first pass of the steam generator, which is the same as the mass flow rate through the second pump, pump 2. There's a lot of these that are the same, but typically the textbook says, let's talk about what goes into the turbine, the first turbine. Okay? All right. So you just do a mass balance. I know that it's a little awkward talking about these. Let's do this. How do I find an equation for how much y is needed? Do I divert 20%, 25%, 15%, 30%? How much do I divert? What's the criteria? Well, you want to divert the maximum to do the most useful good, which is to bring that temperature up of that feed water as high as possible. Well, what would set the maximum? Well, we know the pressures. Didn't we talk about the pressures already? What is the pressure at 6? What is the pressure at 2? What is the pressure at 7? It's all that intermediate pressure. Think about 1 MPa, that intermediate pressure, okay? How high can the energy content or the temperature at 7 be? Because I want to boost that. That's getting into the pump, into the steam generator. What is the maximum temperature at state 7? Could I let it be anything? Could I let it be 440 degrees C? I need it to be saturated liquid at state 7. I'm still working with the concept that real pumps like saturated liquids. That's the best. That's the most efficient. They like liquids. It can be compressed liquid or condensed liquid. That's fine. Subcooled liquid. That's fine. But the limit would be saturated liquid. So the maximum is the saturation temperature at that 1 megapascal. True? That sets it. So we just say that state 7 is saturated liquid. So if I don't divert enough Y is too small, it won't get up to saturated liquid. If I divert too much, it'll be superheated vapor coming out at 7. Not good. I want it to be saturated liquid. So to find the amount Y, what do? I do a energy analysis around that open feed water heater. First I do a mass balance. Okay, if I do a mass balance, what I find is I find the mass flow rate coming down to feed the open feed water heater. Same notation as right here. That's what's in this pipe coming this way. Plus the mass flow rate that goes through the condenser, or something like that. See what goes through the condenser? That's what goes through the first pump. That's what's coming in this pipe. Is equal to the mass flow rate that goes into the second pump, into the steam generator. Oh, that's the mass flow rate that goes into the first turbine stage. Does the mass balance look okay? I know the syntax and subscripts can be a little confusing, but does that look okay? Okay. Look okay? All right. If I divide this whole equation by m dot T1, m dot T1, m dot T1, what is this ratio defined as right there?
Y.
That's Y. So Y plus mass flow rate that doesn't get diverted, that actually eventually goes through the condenser, divided by the turbine is equal to 1. Make sense? All right. We need to do the energy balance for that feed water heater. Okay? Would it be something like this? Would it be the enthalpy coming from state 2 times the mass flow rate of the open feed water heater? That's an N. Plus the enthalpy at 6 times the mass flow rate coming through the condenser. That's an N. Equal to the enthalpy at 7, the mass flow rate that eventually goes into the first turbine stage. Do you like that for an energy balance? Right? Okay. Let's do this. Let's say I can do a couple things at this point for the algebra. I can replace this one by the mass flow rate, first turbine minus mass flow rate open feed water heater. From the energy, not energy balance, from the mass balance. Does that make sense? Let me write the whole equation out. H6 plus H2, mass flow rate open feed water heater, equal to H7 times the mass flow rate of the first turbine stage. So really what I've done is I've used substitution and used the mass balance equation to eliminate the unknown m dot through the condenser. I then do the same thing I've done up here as I divide everything by mass flow rate for the first turbine. Right? And then I see I have an equation H2 times Y plus H6 times 1 minus Y is equal to H7 times 1. I now have an equation for what Y needs to be. True? So a little bit of algebra. Let me see if I can do it here. Y is equal to a ratio of H7 minus H6 divided by H2 minus H6. Is that correct or incorrect? You like it? How many people like it? Look good? So, again, that if I divert Y, if H7 is based on being saturated liquid, okay, then at that intermediate pressure, then I'll get the correct Y, which will give me the maximum sort of benefit from this open feed water heater. Make sense? Here's a problem, but what I would like to do is I like to sketch it. Let's assume that we are operating on 8 megapascal line for the boiler pressure, or steam generator pressure, okay? And then we'll assume it's 1 megapascal for the intermediate pressure, and it's 20 kilopascal for the condenser pressure. All right. Now, where is, let's say we heat everything to about 450, 440 for superheated out of the steam generator. So where is state 1? Isn't it right there? I expand it isentropically. Maybe it lands right there for state 2. I then reheat, maybe I reheat back to 440. That's state 3. Then, what do I do? Maybe I should color code this different. Is that blue hard to see? It's fine? Okay. I just switched it to black. All right. Now we push it through the second turbine from 3 to 4. There's state 4. True? Did I do that correct? Now I put it through the condenser. Where is state 5? Right over here, 5. I put it through the pump. Where is state 6? Right on it, like right there. And I don't know what color to put it to make it more visible. Right there is state 6. All right. Where is state 7? Saturated liquid at the intermediate pressure of 1 megapascal. Is right here state 7? Very good. Very good. Okay. Now I put it through a pump. Where is state 8? A smidgen higher temperature, but the same entropy as state 7. Just like 6 was a little above 5, where is 8? A little above 8. I mean, it's above 7. Then, where is 8? Oh, that's it. It finishes it out. So I could sketch the diagram saying from 8 up to 1. Do I still have some heating of liquid before it starts to boil? Yes. Yeah. And then I have it boiling. Then I have it actually superheating. Then I have it expand, come down. Then I have it maybe heat a little bit till it boils, but most of it in the reheat is superheating. Then I have it expand, and I condense, throwing out condense, 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 down to 5. Put it through the pump. I'm at 6. What happens from 6 to 7? Well, it's mixing. It's mixing. Some of the fluid at 2 was diverted. See that? Some of the fluid at 2 is diverted. The fraction y is diverted. 1 minus y continues on to 3. So it's kind of hard to draw a line, but you're bringing over 2. 2 mixes with 6 to get to 7. All right? 2 mixes. So from 6 to 7, there's no external heating. Energy from high enthalpy at 2 mixing with low enthalpy at 6 to give enthalpy at 7. You ready to solve a problem? Here's the problem. I'm going to set it up and then I'm going to try and do my best in Excel, okay? Let's just say these are the same numbers. What I would do is I recommend you struggle to set it up in a table for the properties as well as a little section of the table for the work and the heat transfers, etc. Let me pause for a minute and set this up. I got to change. All right, so this, hopefully you've written some notes and you know what the problem is and we can walk through the states. But you know that there's 8 states, true, in this problem. And so I even shouldn't have put this column in. Let me take it out quickly. So I put in things like the pressure. Pressure at state 1, well, that was 8,000 kilopascal, true? Usually I can work through the pressures and I get the pressure straight. What about pressure at state 2? It drops down to 1 megapascal or 1,000 kilopascal. How about the pressure at state 3? It stays at 1,000 because it's going in for reheat. State 4, it drops out to 20 after the turbine, second turbine stage. And then it comes out of the condenser still at 20, comes out of that first pump at 1,000, and then it comes out of the open feed water heater at 1,000, and then it goes through the second pump and it boosts it back up to 8,000. Now sometimes I'll do this in Excel. I'll say, you know what, that's kind of the magic number, and I'll just say any time, I don't know why that's not obeying me too well. Maybe I won't show you that. Forget it. Escape. Escape multiple times. It's running too much stuff. In the background it's recording this lecture, and so my processor is old, is decrepit, so hit escape. Maybe I'll do this. That is cell C4, true? If I say equals C4, it'll just get that value. So if I want to change it to 1500 and I want to explore, then it automatically updates. And so I can say get C4, get C4. Likewise, I can say get C3. So if I say, oh, I want to go to 9,000 or 9 megapascal, it automatically updates. Right? So let's leave it at 8,000. And let's leave it at 1,000. And there's a little. If you wanted to do the same thing, this would be equals C6. How many people are familiar with Excel? Very good. You have an advantage. Now, let's work through that state 1. It comes out at high temperature at 440, true? So really, it's the pressure and the temperature that fix state 1. And now the software is going to let me get properties like specific volume. In the interest of time, I'm going to skip that one. I'm just going to get the enthalpy as a function of pressure temperature for water, H2O. And then I have to feed it the pressure. And I know that I need to know the units of pressure because Excel doesn't know units, it just knows numbers. And it's going to be the right units. Same with the temperature, close parenthesis, hit it, and there you go. Can I do that on exam, Professor? No. Sorry, got to go in the tables and do it by hand. But we'll have a project that is, you use the software. And then you say, could you get the entropy as a function of pressure, temperature for H2O as easy? Sure. Pressure, temperature, there it is. I shouldn't show this to you, right? You say, oh, this is too easy. How about state 1? That was after the first turbine. It's pressure and entropy, isn't it? So just say, look, get this value, which is H3 for the entropy. Copy down that entropy. So now I say, can I get the enthalpy as a function of pressure and entropy for water using that value, C4, and H4 for the entropy, true? And there it is. There I have enthalpy evaluated as a function of pressure and entropy. Let's continue on. I know I could get the temperature there and I could get the quality. Let's see if the quality comes up. Quality as a function of pressure, entropy for water, pressure, comma, entropy, close paren. It is slightly in the two-phase region. It's 98.6% quality. Okay? Okay. Now, if I change this to 1500, guess what? That's what the software does. I don't like that number. Okay? So if I change it to, I don't know, 900 kilopascal, it's going to be different quality, different enthalpy as well. But we're leaving it 1,000. Okay. All right. Now, what about state 3? We went back to reheat, and it went back to 440 temperature, true? And so you know what? It's the same pressure, comma, temperature information. If you get good at this, you just copy these. You know, hey, they have the same formula, and they're update. But they're going to update using the values on that row, not, yeah. So that's a little faster. Okay, what about coming out of the condenser? We know the pressure, and we know what about it's coming out at the pressure and saturated liquid coming out of the condenser, true? So if I wanted to know that temperature coming out, I would say Tsat as a function of pressure for water, and there you go. It comes out 60.1 degrees C. We've seen that temperature before. I need that enthalpy. Is it HSat? No. Is it HF? I don't know. What H lick? L-I, yeah, it's HL for liquid. You got to figure out the syntax for whoever coded it up, okay? It's HL for liquid, for water. I hit tab. I want to go get that pressure, and that's H of F. And then this is SL as a function of pressure for water at that pressure. There you go. How about state 5? That was after, messed up here. I messed up. That was state 4, didn't it? So I need to do this one, P sat liquid. And this one, let me just do a copy these. I messed up. How many people were saying, hey, he's off. He's going off on a wrong tangent. But anyway, state 4 is pressure entropy. It's after that second turbine stage, true? So what I'll do is I'll say, you know what, right there, the same formula as I had before. There you go. And I really, I can calculate the quality, and it's 95% at coming out of the second turbine stage. So actually, because of that quality is that it is the temperature is going to be the 60.1. So the temperature is a function of pressure, entropy. This should work. Let's do pressure and entropy. And it works. 60.1. All right, how about state 6? That comes out of the pump, true? So state 6 is out of the pump. Let's do it as a function of pressure entropy, because I know that this entropy is the same. I'm just going to copy. Actually, I can copy. Yeah, I'll copy both of those. And they'll work. They don't want to work, do they? Let's try it again. There. So it copies down to entropy, and then it evaluates that enthalpy as a function of pressure and entropy. Okay? All right, state 7, that's where we mix to get Y, and that needs to be the pressure is known and it's saturated liquid. True? So actually I should color code this back to blue. Color code that back to light blue. And because those formulas are the same, I'm just going to do this. I'm going to copy that and just paste them. And everything goes back to this pressure of 1,000. So now the temperature is 100 and almost 80 degrees C. And the enthalpy coming out of that open feed water heater and entropy coming out of the open feed water heater calculated. Okay, the last state, state 8, after the pump. Well, that's just like state 6 was after the pump. So I'm just going to copy those. And it's pressure and entropy fixed state 8. Okay. That all makes sense. I didn't fill in the whole table, but I'm interest of time. I come over here, the work of the turbine, the first turbine, okay? Well, that's going to be H1 minus H2. How about the Q for the reheat? That's going to be H3 minus H2. So that's how many kilojoules per kilogram that went for the reheat, that went through the first turbine. How about for state 2? The work of the turbine 2, that will be H3 minus H4. How about Q of the condenser for what goes through the condenser? H4 minus H5. How about the work of the first pump? That's going to be H6 minus H1. Not much. What do you mean? I forgot equal. Equal H6. Yeah, it's like, what is going on? I've never seen that before. Tell me it's false. There you go. And then work of the pump, the second pump, it goes from H7 to H8, so H8 minus H7. Now this equation for Y. Somebody tell me it was H what minus H what divided by H what? H what? 7 minus 6, close parenthesis, divided by 2 minus 6. Thank you very much for that help. And so we find that 20.4% of the steam is diverted to feed that open feed water heater, leaving a little less than 80% to continue on through the reheat, through the second turbine, through the condenser, etc. Okay, 8 to 1, which is the boiler, the first pass through the boiler, that's going to be H1 minus H8, true? And now the work net, this I'm going to leave blank right here, because what I need to do is put everything on the same per kilogram basis. Put everything on a kilogram that goes through the first turbine stage. Let me click back to journal to show this. Okay. When you're going to do the work net, you want how many kilojoules of work produced per kilogram of what? Per kilogram that went through the first turbine. Because I can't just add up the work through the first turbine plus the work of the second turbine minus the work of the first pump minus the work of the second pump, because the same mass didn't go through. This is per kilogram of what through the second. So this is the work of the second turbine as a cap W divided by the mass that went through the second turbine. But when I add them, I want them all per the first turbine, so I multiply by the mass second turbine divided by the mass of the first turbine. That cancels. Now I have the work that the second turbine produces based on not the mass that goes through the second turbine, but on the mass that goes through the first turbine. I get everything on the same mass basis. You have to. Well, what is this mass ratio right here? 1 minus Y? No, it's just 1 minus Y, isn't it? It's the fraction. It's like 80% went through the second turbine that went through this first turbine. Okay, so I'll go back to Excel. And I'll say everything I want to be on the first turbine basis. Well, the first turbine, I don't need to adjust anything. For the reheat, though, I need to take that amount and multiply by 1 minus the fraction, because look at these two numbers. I know I make 600 kilojoules for every kilogram that goes into reheat. I didn't make it, I spent it. But I want it per kilogram that goes through the first turbine. All right, let me continue on. So this is equal to this amount times 1 minus, I should have just put 1 minus Y as a separate parameter, but there you go. And then the condenser, that times 1 minus Y. Whoops, I'm trying to type Y. There you go. And then work of the first pump, that times 1 minus y. How about through the second pump? Everything goes through the second pump, just like everything went through the first turbine. True? Now I'm ready. Let me do the boiler. Everything goes through the boiler, the first pass. Now I'm ready to calculate Q net, because everything is now per unit kilogram that went through the first turbine. It's going to be equal to the work of the turbine first stage plus work of the turbine second stage minus the work of the pump, first pump, minus the work of the second pump. There it is. Did I mess up? No. Okay. Q net. Let me calculate Q net. Okay. Q net is the net heat in. So I have the reheat is in, and the boiler first pass is in, but I have a rejection in the condenser, so I need to subtract that. Minus this in the condenser. Is that going to equal W net? Is it going to be 1163.7? This is where I get nervous. I have no idea. I hope that I make an error. I didn't make an error this time. I've made plenty of errors. Yes, sir.
That column, what is that called again? Is this per kilogram of the turbine work?
Through the first turbine, yeah. They explain it well in the book, so please read that as well. Let me finish this out. Q in equal to the reheat plus the amount in the first pass. Now I can calculate the thermal efficiency. It's the net work divided by the Q in, and I can calculate the back work ratio, which is the sum of the two pumps divided by the sum of the two turbines and we have now answered all the questions that we set out to answer. And I see I'm ending spot on time. I'll be in my office if you have any questions. Thank you for your attention. 1 week from today, what do we have? First exam.